All right, let's dive in. A new paper just dropped from Google Quantum AI, and it's a big one. They're making a pretty significant claim about our ability to probe the really chaotic, complex dynamics of many-body quantum systems. And look, this isn't just some small incremental step. It feels more like a fundamental shift in how we can even see, let alone use, the incredibly intricate correlations that define the quantum world. So let's break down exactly how they pulled this off.
Okay, so here's our game plan. We're going to tackle this in 5 parts. First, we need to really understand the core problem everyone's facing, something called quantum scrambling. Then, we'll get into the author's really clever solution using what are called out-of-time order correlators, or OTOCs for short. From there, we'll dig into the actual experimental data that shows how sensitive these things are before we hit the main event, the discovery of what they call large loop interference. And finally, we'll tie it all together and talk about what this means for the big goal, achieving practical quantum advantage.
So let's get right to it. What's the fundamental challenge here? Well, in any complex quantum system with lots of interacting parts, information doesn't just sit still. It scrambles. It spreads out like a drop of ink in water, and it becomes incredibly difficult to track. And this scrambling process, it's a massive roadblock for pretty much everyone, experimentalists trying to measure these systems, and theorists trying to build models of them.
And this slide, it just visualizes the problem perfectly. See at the bottom, you start by poking just one qubit. But in what we call an ergodic system, which is just a fancy way of saying a system that explores all its possible states over time, that single bit of quantum information just explodes. The entanglement grows like crazy, and the information gets smeared out across the entire Hilbert space. You know, that mind-bogglingly vast space of all possible quantum states? It becomes delocalized, and for all intents and purposes, it seems like it's just lost.
Now, this scrambling is exactly why our standard tools, things like time-ordered correlators or TOCs, are just not up to the job. As you can see on the left, their signals just die off exponentially fast. They lose their sensitivity almost instantly. So this sets up the big research challenge, right? We desperately need a new kind of probe, one whose signal decays much more slowly, algebraically, so we can stay sensitive and actually see the rich hidden correlations that are playing out in these long-time dynamics.
So how do the authors crack this nut? Enter the out-of-time order correlator. The key insight, the really beautiful idea here, is to stop thinking about quantum evolution as a one-way street and start treating it like an interferometer.
This diagram from the paper really gets to the heart of it. An OTOC protocol isn't just about evolving the system forward in time. You evolve forward, you poke the system with a perturbation, and then, and this is the magic trick, you evolve it backward in time. It's like hitting rewind. This time reversal makes different quantum histories or trajectories interfere with each other, and that interference is what lets you cancel out all the noise and amplify the really subtle correlations you're actually trying to see. So, for those of you who want the formal definition, here it is. An OTOC is basically a measure of how much two operators applied at different times fail to commute with each other. You apply one operator, M, at the very beginning, then you let the system evolve, you apply another operator, B, and then by seeing how B's presence affected the final measurement of M, you can precisely track how that initial perturbation spread or scrambled through the whole system.
So how do you actually measure this in the lab? You use what's called an echo sequence. Step 1, you let the system evolve forward. Step 2, you poke it somewhere else with a simple Pauli operator, B. Step 3, you reverse the evolution. You hit rewind by applying the conjugate unitary, U dagger. And finally, step 4, you measure the original operator M. At the end of the day, this whole process is really just asking a simple question. Did the poke I made in step 2 mess up the information I'm trying to get back from step 1?
Okay, so that's the theory. It's a beautiful idea. But does it actually work in practice? To find out, the authors ran these protocols on a superconducting quantum processor to rigorously test whether OTOCs are really as sensitive as they claim.
So here in panel A, you can see the actual quantum circuit they used, a mix of random single-qubit gates and some fixed two-qubit gates. But the real money shot is in panel C. This plot shows the standard deviation of the signal they measured, averaged over many different runs of the circuit. Now, why does that matter? Because the standard deviation, the fluctuation, is a direct measure of how sensitive your observable is to the tiny microscopic details of the circuit. A bigger fluctuation means more sensitivity. And this chart, well, it just lays it all out. After just 15 cycles, look at the standard TOC. Its fluctuation has basically flatlined. It's gone to almost zero. It's blind. The sensitivity is gone.
But now look at the OTOCs. Both the first and second order versions are still going strong, with significant fluctuations. This is the smoking gun, the clear experimental proof of a slow, algebraic decay versus that useless, rapid exponential decay of the TOC.
So the big takeaway from this data is that the whole time reversal interferometry thing isn't just some clever mathematical trick. It is absolutely essential. It's precisely this feature that lets OTOCs see what standard methods can't, holding on to their sensitivity long after other signals have just faded away into the background noise. This, right here, is the key that could unlock the physics of long-time quantum chaos.
Okay, so this enhanced sensitivity is cool, but what it lets them see, that's the real bombshell of this paper. The authors found that a specific, higher-order version, which they call OTOC2, can reveal a type of quantum interference that is completely invisible to any of the simpler probes.
You have to understand this schematic. In the Heisenberg picture, our operator B evolves into this wild superposition of many different Pauli strings. You can think of a standard OTOC as measuring what they call small loop interference, where these different quantum paths recombine in simple pairs. But OTOC2 is a whole different beast. It involves 4 copies of the operator, which allows for this much more complex, large loop interference. Think of it like a 4-way intersection, where 4 distinct quantum paths all have to meet at the exact same time and interfere constructively. It's a fundamentally richer, much more delicate kind of many-body correlation.
But how do you actually prove that this delicate 4-way interference is really happening? Well, they designed this brilliant protocol. They started inserting random Pauli operators all throughout the circuit. This is basically like putting a random phase shifter in an interferometer. It doesn't change the amplitude of any single path, but it completely randomizes the phase relationships between them, effectively scrambling any interference pattern.
And the results in panel C are they're striking. See that yellow curve C4? That's our special OTOC2 signal. The second they insert those random Paulas, boom, the signal just tacks. It drops like a stone. That proves that constructive interference was making up a huge chunk of that signal. Now contrast that with the blue curve for the standard OTOC. The effect is way, way weaker, which confirms it's mostly just seeing that simple, small loop stuff, not these complex, large loop effects.
So this brings up the million-dollar question. Couldn't a classical supercomputer just fake all this? Well, this table compares the experimental signal-to-noise ratio against a leading classical algorithm. And for the standard OTOC, C2, you can see the classical simulation actually does a pretty decent job. It almost keeps up. But for that special off-diagonal part of OTOC, the part with all that large loop interference, the classical algorithm just falls on its face. It fails spectacularly, an SNR of 1.1 versus the experiment's 3.9. This thing is genuinely hard for a classical computer.
And look, this classical hardness isn't just some academic curiosity. It's not just about showing off. It points directly, concretely, toward a viable path for actually demonstrating practical quantum advantage.
So, to really drive this point home, they decided to go big. They scaled the whole experiment up. This plot shows OTOC measurements on a 65-qubit system. Now, at that scale, you are firmly beyond what any classical computer on Earth can simulate exactly. You're in a whole different league.
And when I say a different league, what do I mean? Get this. The authors estimate that to simulate just a single instance of one of these 65-qubit circuits would take the Frontier supercomputer, the fastest one in the world, about 3.2 years. The quantum processor collected the same data in just over 2 hours. That's just mind-boggling.
But here's the so what question, right? It's fast, it's hard to simulate, but is it useful for anything? And the answer is yes. The paper demonstrates a really neat proof-of-principle application in something called Hamiltonian learning. The basic idea you see here is to use the quantum processor as a simulator to figure out some unknown parameter of a physical system, just by matching its OTOC2 signature.
And it worked beautifully. Using the data from their quantum processor, they built a cost function that had this clear, deep valley right at the correct target value. This isn't just some toy problem. It's a real demonstration that the incredible sensitivity of OTC2 can be harnessed for a practical, relevant task.
So when you put all of this together, what they've really found is an observable that lives in this perfect Goldilocks zone for quantum advantage. First, it's measurable. You can actually get good data with high accuracy on the hardware we have today. Second, it's classically hard. Even our best algorithms struggle with it. And third, it's practically relevant. You can actually use it to do something useful, like learning about a physical system.
And that brings us to the final big question. The paper makes a really compelling case that this specific kind of many-body quantum interference isn't just some scientific curiosity. So the question we're all left with is this. Is this it? Is this strange, constructive, large-loop interference the key observable we've been looking for? The thing that will finally let us move beyond academic benchmarks and start solving real-world problems with quantum computers?